I'm super excited to be here today with everyone to be able to share a little bit of my lab's work in hopefully building the next generation of tools for software engineers to help build more complex systems that are more correct, efficient, and secure. So before I get into talking about my research, I'd like to give a little bit of background about myself since this is my first year at UCF. So I completed my undergraduate degree in physics from the College of the Holy Cross in 2013. I minored in computer science, decided that that was way more interesting to me. So I decided to pursue my master's and Ph.D., which I earned at William and Mary in computer science with a focus on software engineering research. And I also completed a postdoc at William and Mary for a couple of years, actually while my wife was finishing up her PhD. So in 2020, I started as an assistant professor at George Mason University and spent my first few years as a professor working from my home office, as many of us did during the pandemic. And I'm really excited to this year have joined UCF as an assistant professor to bring my lab's expertise in software engineering to the university. So I'm in the Department of Computer Science, and I'm also a member of the Cybersecurity and Privacy Cluster, since a lot of my work does touch on computer security and privacy. My general research interests, as I will discuss, are software engineering, maintenance, and evolution, applications of machine learning to building developer tools for software engineers, and also helping to automate and ensure software security from a developer's or engineer's perspective. So my teaching interests span programming. So I'm currently teaching an introduction to programming class in the C language, which has actually been a lot of fun. It's the language I initially learned to program in, as well as different courses in software engineering, design, and testing. So I've listed a few key achievements and awards there. I've been lucky enough to have a few distinguished paper awards, and I was recognized with the Rising Star Award from one of my research communities last year. And a little personal tidbit about myself. So I was a competitive rower for the better part of 10 years in my collegiate career. That photo is from the Head of the Charles in Boston, where we competed, and I believe we got in the top 10 in that race. So I am still kind of involved in the rowing community a little bit, not as much as I have been in the past, but I've both rowed and coached in the past. So my research lab is the Software Automation, Generation, and Engineering Research Lab, or the SAGE Research Lab. And I currently have six fantastic PhD students. Two of them came with me to UCF. Four are finishing out their studies at GMU. And we've also been quite fortunate to be a fairly well-funded lab. So over our first 3 years, we've been awarded over $4 million in research funding from both government and industry sources. And I think one reason for that is, we build tools that we try to prove out in industry. So we try to put our tools in the hands of real engineers and get feedback as to whether or not it's actually helping them to do their jobs better, which is a really challenging but rewarding process at the same time. So I would like to kind of give a brief kind of general introduction to my research ethos before I start to talk about a few specific projects. So my research is in the general area of software engineering, which means that I study the methods and techniques that developers use to design, create, test, and manage software. But this is a very broad field. And within this field, my specific research goal is to try to develop tailored automated approaches or automated tools that help to facilitate developer needs throughout the software development and maintenance lifecycle. So the key question then becomes, how can we design these tools that are practical for developers and help to introduce some useful automation into their jobs? Well, most recently, my work has turned to a combination of mining the wealth of information that we have access to in software repositories. I think we're quite lucky in the field of software engineering in that we have an unbelievable amount of data that exists in software systems that are developed in open source communities. So we have access to, years of software development, history and activity that exist in these online sources. And within these repositories, there's different types of information that we can use. There's textual software artifacts like source code files themselves, but also other things like documentation that's written in natural language, or bug reports that are, describing issues in the software. And beyond that, we also have other multimodal types of software artifacts, things like design documents that might be figures, things like screenshots or video recordings of user interfaces. So what my research tries to do is we try to mine this information from software repositories, take this all together, and we aim to then both apply machine learning techniques, conduct empirical analyses of this data, and apply program analysis techniques in order to learn different patterns from this information. And this allows us to build this developer-centric automation that I've been talking about, tools that specifically target needs of developers that are informed by this incredible amount of data that we have access to. And as I said before, my lab has a strong focus on practical significance. So we want to try to blend scientific discovery with actual utility for real-world developers. So that as while we hope to break new ground scientifically, develop new techniques, and make theoretical breakthroughs, we also want to ground a lot of our work in practical significance so that developers at top companies can benefit from these scientific breakthroughs that we're making. So I'm going to talk about 4 general research areas that my lab is involved in today. We do have other projects that I won't have time to get into, but I think these are some of the more exciting areas of work that we're currently working on. So the first type of research is on automated UI analysis. So the main motivation for this is, when you are using your smartphone or any type of computer, application, you're typically using that through some sort of user interface. And these user interfaces have a wealth of information about the functionality of programs. So you can glance at your smartphone or some sort of UI and generally intuit, if it's designed well, what the different functionality is for that particular program. And interestingly, what we found is that this information is often completely orthogonal or encodes different types of information compared to what is in source code, which tends to be more technical, or even design documents in software repositories. So the main idea of this general research project is to develop techniques to learn patterns from user interfaces, combine this with other patterns that we learn from different types of information sources, and use this to build automated tools. So one example of this is a tool that we built for basically taking a screenshot or like a Figma design document of a user interface, comprehending the UI using different computer vision techniques, and then automatically implementing the code for that user interface using some different machine learning and deep learning techniques. But more broadly, we have several different projects that are related to UI testing, automated code comment generation for documenting code, detecting dark patterns, and even automated evolution of UIs. So we want to basically develop bespoke deep learning techniques to perform some of these different tasks, and we aim to use different multimodal transformer-based models. So we've done quite a bit of work in this area. So we have 17 different publications, 1 distinguished paper award. We have over 11 research prototype tools and 3 fully large-scale open source data sets that we've developed as part of this, and we're continuing our work on this. And additionally, one of the tools that we've created for developing UI, or for detecting UI issues, was actually deployed at a large multinational telecommunications company and is currently being used by hundreds of developers and designers. And we've also had another tool that was just recently, in the past 6 months or so, deployed at a software testing company. So the next research area that I'd like to talk about is our lab's work on trying to improve bug reporting. So as software has increased in complexity over the years, One thing that has not evolved to keep up with this are issue trackers, which is where developers or users go to report problems about software. These essentially are still just a text box where people go and try to hopefully capture the essence of the problem that they've encountered in software. And really, because of the the lack of automation and the relatively rudimentary design of these issue trackers, we have many empirical studies in software engineering that show that these bug reports and issues are often of very low quality, and they're hard for developers to reproduce, localize, and fix. So we aim to essentially transform this task of bug report management by introducing automation. So one part of this project that I'm going to show in just a second is actually trying to create a chatbot interface for end users to more reliably report software issues, as well as an interface for developers to more quickly write bug reports. So the main idea for this is that a reporter, be it a developer or just a normal end user, would interact with one of our two systems, either BERT or eBug. We would automatically, in real time, parse natural language that they're entering into a text box to describe an issue. We would automatically map this natural language to different information from the program, and then use this to predict what they are going to describe in their actual issue report to try to help facilitate and automate this process. And this will happen as they report different steps to actually reproduce the problem until at the end, we get a high quality bug report out in the end. So this gives an overview of some of the different techniques we use, such as neural sequence labeling and dependency parsing, as well as automated static and dynamic analysis of applications. And in the end, we're able to generate these extremely detailed bug reports that are very easy to reproduce. So this is a quick demo of one tool that we built. This is end user facing. So we tried to create this in a bit of a friendlier user interface. But essentially, as this user is typing, our technique is automatically parsing this information and is trying to relate this back to program information. And it's able to predict which screens are most likely to be affected by what that person just described as an issue here. And for developers, they're not going to want to interface with the chatbot, but we can help to autocomplete certain information that they might be typing in a given program using different sorts of predictive deep learning models here. So these are just two kind of full-fledged research prototypes that we've built in this area. So I've gone over a lot of the objectives here, but the main achievements to date is we have 16 publications, another distinguished paper award, a few different research prototypes, and a data set that we've developed here. And our tools have shown that they improve the quality of reports. We've done human studies that have essentially shown this. And our work on bug triaging and localization is currently state of the art in the field. We have an upcoming paper at one of our top conferences this spring where we'll present some of these results. So the next project is building developer tools for software security. So again, because of this increase in complexity of software that we're seeing, developers need automated tools to assist in security assurance. And currently, it's not even clear how much we can rely on existing tools that provide some sort of security guarantees. There's all these soundness issues about how much developers can actually trust these tools. And furthermore, some domains like IoT or smart home programming don't even have mature tool sets to help handle software security. So we aim to both improve software tools by adapting techniques from software testing, in particular mutation analysis. And we aim to create new software tools for emerging platforms like the Internet of Things. So we are really blending together here ideas that were developed in the field of software testing and applying them to help provide better security tools for developers overall. And on the IoT side, we're trying to create models of how end users interact with IoT devices to provide developers with additional resources to check how their different security and privacy implementations for those systems actually function. So we've got several publications again for this research topic, and some kind of interesting things related to this is, we found three critical security vulnerabilities in smart home platforms, which have since been patched. So things like Philips Hue and the Casa smart home ecosystem and Samsung SmartThings. We've also identified and fixed numerous different flaws and vulnerabilities in industrial strength, cryptographic analysis techniques, static analysis techniques. And we've also developed a model through some user-centered research that really tries to nail down what practitioner needs are related to static analysis tools. So the last area that I'll talk about, and the most recent area for me, we just got an NSF Medium grant on this topic, is trying to build tools for interpreting basically AI-powered tools for programming. So these large language models, which we've all heard so much about recently, have taken the software development world by storm. In talking with engineers at Google, they tend to estimate that as much as 40% of recent production code, so this is code that you have likely used in some Google product, has been generated by AI in some way, shape, or form. Now, the issue with this is, these tools are still somewhat nascent, even though they're very rapidly developing, and it's very difficult. It's a known problem. It's very hard to interpret why these tools are making certain decisions. And because of this, developers don't always trust them. So we aim to essentially try to fix this by developing new techniques for both interpreting and explaining predictions of neural models of code. So we aim to do this both by developing a causal inference-based framework that maps predictions of these code models to concepts that humans can understand, as well as adapting explainability techniques from the NLP domain, such as LIME, shapely values, integrated gradients, to explain the prediction of large language models for code in software engineering contexts. So we currently have 3 publications under review for this work, but we're extremely excited about the impact that this can have. And we think that this is going to continue to be a really important topic in the area of software engineering. So these are kind of the 4 areas that I will discuss today. Future work, we aim to kind of continue going along these lines. We'll focus on human studies, and I'm also working towards automating UI accessibility compliance as part of the work on UI analysis. And I'm also interested in, software development for emerging platforms like AR and VR, obviously these interpretability techniques and security-focused tools. If you're interested in collaboration, human studies of programmers, software accessibility, computer security topics, or if you're looking for interesting applications of machine learning or computer vision techniques that you're developing, this could be a good place to try out some of those ideas on this awesome amount of data that we have. So I, can't end this presentation without thanking my fantastic team of students who have, contributed, enormous amounts of effort and time to this work to make the lab as successful as it is. And this is a very small set of collaborators that I have worked with, but some of the ones that I've worked with more recently. And of course, I'd like to thank them as well. But with that, I will end, and I'm more than happy to answer any questions. Thank you.